Hello, welcome to Livy's Ranger Garage. On this YouTube channel, I hope to produce a series of videos teaching you about automotive electrical systems. We will cover basic electricity, how to troubleshoot electrical problems, and how to add and modify circuits in your vehicle. These videos are primarily aimed at owners of Ford Rangers, Explorers, and Bronco 2s, but most of the principles here will also apply to other vehicles. My name is Eric, and this channel is named for my dog Livy. I hope you find these videos useful. Thanks for watching.
This is Lesson 1. In Lesson 1, we need to learn a few basic terms. Some common terms used in electricity and blueprint reading and things like that. And once we get through this little boring section, everything else will make a lot more sense to you. Let's start with voltage. Voltage is defined as electromotive force or a difference in potential. And all that means is that we're measuring or we're talking about a difference in electrical energy from one location to another. You may remember from science class way back that all atoms have electrons, and some atoms and molecules have extra electrons and some don't have enough. Well, we use chemistry in a battery, in a vehicle, or an alternator or a generator to produce excess electrons in one place and then move them through circuits to areas of less electrons. So voltage is, like I said, it's defined as an electromotive force and we'll talk more about that later, but basically it's force, just like force that you would put on a torque wrench or something like that, except this is force that is generated by electricity. The unit of measurement for voltage is the volt, and you'll usually see that abbreviated as a V or sometimes as an E for electromotive force. So that is the basic unit that is driving what we do with electricity in our vehicles. The next term we want to define is current. Okay, current is a measurement of the flow of electricity from one location, or the movement of electrons in a circuit. So that's all it is. So we have the voltage is a force, and if we give that force a path through a circuit, then the electrical energy can flow, or it can move. So think of current as flow. We'll call it a flow of energy. And the unit of current is the amp, or more formally it's the ampere, and that's named after I believe a French scientist. His last name was Ampere, and you'll see it abbreviated as an A. Alright, our next term is resistance. Please forgive my sloppy handwriting. Maybe I'll get better at writing on the whiteboard as these lessons progress. And resistance is just that. It's a resistance to the flow of current, or an opposition. To the flow of current. I'll try to keep things centered on the board here for you. And resistance is measured in units of ohms. And that's named after another scientist. These guys way back when like to name things after themselves. Now the abbreviation for that is the Greek letter omega. You've probably seen this before. So that's resistance. When we do all that and we have a flow of current and we have our voltage available and it's going through a load with some resistance, we end up doing work, electrical work. And we measure that. We talk about the power of a circuit. Okay? The power is the rate of transfer of electrical energy. So it's measured by how much energy moves in a period of time. So let me write that up here. The rate of transfer of electrical energy. Power is measured in watts. And you guessed it, I'm pretty sure that's another scientist's name. And the abbreviation is the watt. Or sometimes, if you ever look at your electric bill at home, you'll notice that you're charged for your electricity in kilowatts. That would be kW, the kilowatt. Oops, sorry. And that's just 1,000 watts. What else did I want to say about energy? Oh, okay. I talked about it being the rate of transfer of electrical energy, and that energy is often measured in joules. Yeah, another scientist name. So 1 watt equals 1 joule of energy transferred in 1 second. 1 joule per 1 second. And that's where all that comes from. And one of the next things we need to define is a circuit. Okay? As we talk about electricity, we are almost always going to talk about circuits. And a circuit is just a path, usually through a conductor, okay, it's a path through a conductor for current to flow from a high energy location, from a high energy source to a lower energy. And please don't get picky on me on these definitions. Like I said, these are simple. This is just to help you get started and help you to understand what we're talking about as we go on into other lessons. So as we talk about the circuit being a path for energy to flow, I did mention something else here, a conductor. Okay, and conductor is just something that conducts electricity. Usually a piece of wire, but also in your vehicles we use the steel body and frame of the vehicle to conduct electricity also. And you'll see that later on as we go through some diagrams. As we talk about a circuit, let me just show you a simple one. Okay, we'll start off with a battery. This is the electrical symbol for a battery, and we'll call that the positive side and that the negative side. I'm sure you remember that batteries have a positive terminal and a negative terminal. We'll even label this. This is 12 volts DC. And we'll talk about that later, but DC just means that the current flows in one direction only. That's direct current. In your house, when you plug something into the wall, you're getting electricity that flows in both directions, and they call that alternating current. That's AC. So anyways, to have a circuit, the very most basic circuit we could have would be to have a source, our battery, and to have a load, and we'll call this a light. And then we go back to the lower side, the lower potential side of the source. When I talk about voltage or sources a lot, I'll talk about a higher potential side and a lower potential side. And potential is another term for voltage, another way to talk about voltage and the energy that's available or potential to do work in a circuit. Now, of course, and we'll get into this more later as we look at actual automotive circuits, but this isn't a very safe circuit and we don't have a way to control it. So a lot of times in a circuit we will add an overcurrent protection device, usually a fuse, sometimes a circuit breaker. The fuse looks like that, and we'll label this F1 and we'll say 3 amps. That's the rating. So if our current goes more than 3 amps, then this fuse will blow. It'll open, and we will no longer have a circuit. We will no longer have a closed path or a closed loop for current to flow, and we call that an open circuit. And of course, at that point, the light goes out and no more current flows. But let's put our fuse element back in here. All right, and then the next thing we need is a way to turn the light on and off. Usually we'll do that with a switch. And a switch is often drawn like that. Okay, that's supposed to be a little arrow. Okay, and that shows the switch open or in the off position. Let's go ahead and label that. That's S1. And if we want to turn the light on, we would close the switch. And that's how it's drawn, for the circuit to be closed and for the current to flow through that circuit. Now we have a safe circuit, a very simple circuit. I've got one over here on my workbench, and I've got a photo of it right here. We've got a couple more terms we're going to define, but before we go further, I want to give you the relationship between voltage, current, resistance, and power in a circuit. And you've probably heard about this before in science class. And when we go back to that scientist, Mr. Ohm, and he developed a scientific law, a law of physics. And Ohm's law brings together voltage and current and resistance. And what it says is that voltage is equal to the current times the resistance in the circuit. So if we have a resistance or a current of 1 amp and we have 12 ohms of resistance, that would equal 1 times 12 equals 12 volts. It's that simple. This is very simple multiplication and division in most cases. Some electricity gets into other trigonometry and stuff like that later on, but we're not going to get into that. If we do, it'll be in another lesson and you'll be ready for it by then. So that's very simple. You can see if we have 12 volts and we have 2 amps. Okay, and we want to solve for the resistance. Well, what we could do is say the resistance is equal to 12 volts divided by 2 amps. And that means the resistance is either equal to 6 ohms. So you can see we can manipulate the basic formula to solve for whatever part of it we don't have. If the voltage is equal to the current times the resistance, and we just saw the resistance is equal to the voltage divided by the current, and we can say the current is equal to the voltage divided by the resistance. Now you notice earlier I also talked about power, and we don't see anything up here about power. And I'm going to include this with our Ohm's law lesson here. I don't know if it's technically part of Ohm's law or not, but we're going to cover it here. Okay, power is equal to voltage times the current. Oh, I don't think I told you that I is also an abbreviation for current. Okay, so there it is. That stands for current, the I there. So let's see, if we have 12 volts and we have 2 amps, then our power is equal to 24 watts. That's all there is to it. Now, if you remember what we did with Ohm's law a minute ago, you know we can solve for this a few different ways. We can also say that power is equal to something else. If voltage, okay, with Ohm's law we said that E equals I times R, and we also said I, the current, is equal to voltage divided by resistance. So we could say, we could substitute this up here for voltage. So we could say that voltage, or that power, is equal to current times resistance times current. And you see we have current twice there, so that would be the same as saying power is equal to I squared, that's I times the resistance, or current squared times resistance. That's a very common calculation right there. We could also say, if we do substitution like that, we could say that power is equal to the voltage times, and from down here we know the current is voltage divided by resistance, right? So if that's voltage divided by resistance, and then we could say that that's power is equal to voltage times voltage divided by resistance, or in other words, voltage squared divided by resistance. That's not quite as common, but you see how this works. If you look around on the internet, you will see some places where people draw out a whole big circle like this. They divide it into 4 sections, but you'll see all the different manipulations of these calculations all written down in a circle like that where it's easy to refer to. If you're going to do much of this, which it really isn't necessary to do a lot of calculations in what we're going to do with automotive electricity, but if you're learning this for school or something like that, you may want to find that circle and print it out or save it on your computer somewhere where it's easy to refer to until you get it memorized. We're almost finished with terminology. One of the next things we want to talk about in automotive electricity is a solenoid. You may have heard of this. A solenoid is a very simple device. It's a coil of wire, usually with a hollow hole in the center with an iron slug that can move inside, and that iron slug is usually spring-loaded so that it returns to position. But this coil, when you put electricity to it, it forms an electromagnet. And so we can use that to do work. Let me just draw a coil here. I'm not great at drawing. Okay. And this is our coil. And in the center, let's say we have an iron bar. And that iron bar is attached to a spring that is attached to the frame of the solenoid. When we put our voltage across here, we put 12 volts here, and we attach this to 0 volts, so we have a potential of 12 volts across our coil. It forms an electromagnetic field in the coil, and that attracts this iron bar. And it will try to center it. It'll pull it up, or pull it in, or whatever you want to call, and it'll try to center it. Let me draw that over here. This is the same coil. Okay, and instead of our bar being down there, now our bar will be up like this. Because that electromagnetic field is attracting it. And there's our spring. Well, we can use that to transfer electrical power into mechanical movement, linear movement. It moves back and forth linearly. And that's what a solenoid does. It converts electrical energy to mechanical energy. And that's useful. We can use this iron bar, we can attach that to something, and let's put a little lever arm here, and it can, let's say we have another arm back here that's attached to a wire, maybe with voltage on it. And we've seen a signal or a symbol like this before, haven't we? And when we can have this be another electrical contact here, so this looks like a switch, doesn't it? And then this would go out to our load in our circuit. Well, if we do that, and we use this moving iron bar to move that electrical contact and make it, or to move that switch and make it close, then we can transfer electricity from one through our circuit. And when we do that, we have taken a solenoid and we have created a relay. And that's why solenoids are important. We use them for other things in machines and vehicles, but for what we're going to be talking about in these lessons, the relay is the more important thing. So if we do that, and then over here on this first drawing of a solenoid, okay, and I should have left a little more space, but anyways, then we'd have our contact over here attached to our iron bar, and you see it's open. The contact is open. And what we've created here is a simple relay, and we use these all the time in the automotive electricity. I just happen to have one. If you've looked in your in the fuse panel under your hood, you've probably seen something like this. And there it is, and you can even see in here, let me get a pointer. Okay, here's our wire going through our coil and coming out, and then here's our electrical contact. And this is showing it closed to terminal 87A and open to 87. And when we energize this, it will switch that. It will make that open from 30 to 87A, and it will close the contact from 30 to 87. So it turns one circuit off and the other circuit on. And that's a 5-terminal relay. And we'll see that later. Well, we'll talk about relays a lot later when we talk about connecting accessories and adding lights and things to our vehicles. Before we bring this lesson to a close, I just want to talk about a couple of the specialized tools that we use dealing with electricity and things that we're going to need for some of our lessons. The first, and of course you'll need some simple tools like screwdrivers, a flathead screwdriver and Phillips head screwdrivers and pliers and things like that. But specifically for electrical things, one tool that is used quite often is a multi-tool like this. And this is a combination of wire stripper. That's this section right here with these different size holes, and you see numbers next to them that correspond to different size wires. And this also has several different places where you can cut wire. Here's one section here for wire cutting, and there's another section up here. And then these 3 areas here are for crimping connectors onto wires, and I'll show you how to do that in another lesson. And this is another crimper. This is a little more specialized. I think that's for ignition wires. And then this tool also has a place here. These holes are threaded on one side, on one of the jaws, and not on the other. And you could screw a small screw in there, like a number 8 screw with 32 threads per inch. You could screw that in there, and as it comes out the back side, you get it to the length you want, and when you close it, it'll cut that screw, and then you have a shorter screw. So sometimes you've got a screw that'll fit, but it's way too long, and instead of stacking washers or something like that, you can cut it to length. So something like this is very, very useful. It does a lot of different jobs, and if you get a good one, it does them fairly well. Here's another version of that. This is an older, cheaper version. You can see it's not as good. They didn't paint the numbers for the different markings, so it's a little harder to read. But it still has wire cutter and crimper section, the screw cutter, and wire stripper sections here. So, I mean, if you've got one like this, it'll work fine. You can use that. You may have one like this that just has stripper sections and a cutter. That's fine too. Here's a tool. This has a cutter and crimper, but this doesn't do any wire stripping. It's strictly for cutting wire and for crimping insulated and non-insulated terminals. Here's another tool. This is specifically for stripping wires, and for this one it just has one stripper section. It does have a cutting section back here, but you notice up in there the hole gets pretty tiny. If you need to adjust that, you loosen this screw and move it up and down in the slot until it stops the jaws from closing any bigger than you, or any smaller than you want. Because you don't want the jaws to close too small on your wire. If you have a big wire and you close it this small, you'll cut into the wire and it'll become weak and break there. Plus, it will not conduct electricity as well as it should. It will conduct less current. Bigger wires conduct more current, smaller wires conduct less current. And finally, I've got one of these. I hardly ever use this. These are expensive and they're fancy. But this is an automatic stripping tool. All it does is strip. But you can see it has a different size holes for different size wires. And then back here on the other jaw, it has a clamp that comes down. And what that does is, let me find a piece of wire. Here's one. So if we put this in right, I gotta get the light right so I can see it. I believe that's going to be 18 gauge. Okay, so I stick it in like that. As I start closing and squeezing the handles, you see the clamp comes down and holds it, and then the jaw comes shut and cuts through the insulation, and as I keep squeezing, it pulls it apart. So it automatically strips the wire. And I'll show you that again. I'm squeezing the handle and it goes like that. So if you have one of those, that's fine. They're fun to play with and they work great, but that's a pretty expensive tool that you really don't need. I just happen to have one that I've had for probably 25 years, and like I said, I hardly ever use that thing. Now the next important tool we need is something to measure voltage and current and resistance with. And one of the simplest tools for automotive things, for 12 volt circuits in a car, is a test probe like this. And you see it has a sharp probe here that you can sometimes even poke into wire insulation to touch the wire inside. And in here, it's hard to see, but there's a little light bulb in there. And then that's connected to a wire that comes out with a clip that you can clip on the body of the vehicle or a ground terminal somewhere. So you can clip this to ground and then go and touch different parts, different components and things. And if the light lights up, then you know there's a difference in potential. You know there's voltage available at that place that you touched with the probe. These things work great. They're very, very inexpensive. They're easy to find. You can get them at Lowe's, Home Depot, AutoZone, Advance, O'Reilly's, whatever. They're all over the place, even Harbor Freight. So they work good, but they don't tell you how much voltage is there. And all they tell you is that there's a difference in potential that's great enough to light that light inside. If there's less voltage, the light will be dimmer. If there's more voltage, the light will be brighter. But you really don't know how bright or how much voltage potential there is. So to do better measurements, we usually use a multimeter. Now this is a fancy one. I have this because my career is in electricity and industrial maintenance, so I keep a good quality meter with me most of the time. But you can see it has two test leads. These are called test leads with probes, and you can touch one to ground and one to a terminal to see if there's voltage there. You turn it on and set it to the right scale. This is the scale for reading DC voltage. No, that's not what I want. There we go. Turn the light on. Maybe it's easier for you to see. Here's a scale for reading millivolts. That's really tiny voltages. Here's a scale for reading resistance. You see the omega for ohms. And right now, when a digital meter like this reads OL, that's overload or whatever, and you see the M over here next to the ohms, that means that the resistance is so great that it can't measure it. So that's infinity, or just too many ohms. But look, when I touch it together, now we should come down. Eventually this will settle out right on 0 ohms. Sometimes you can even adjust them, but I might have a little bit of dirty connection there on my leads or whatever. But you see, different resistance gives you different readings. And then we have some scales over here for reading current. You see amps or milliamps or microamps. That's just different ranges. And there's a lot of other functions on this meter. But you don't need a meter like this that costs several $100s. You can do just fine with one that costs just a few dollars. They range in scale anywhere from, say, $4 or $5 right on up to thousands of dollars. Here's one I ordered. Oh no, I got this one at I think Harbor Freight, and I'll turn it on there, and it's set on the resistance scale. So you see this one, it just shows that when it's not touching anything, when there's infinite resistance. And I touch the leads together and you see it's slowly coming down towards zero. Again, it may not go exactly to zero, and that's just because of the resistance of the wires and the connections and how hard or how good a connection I have when I touch the leads together. It has several different voltage scales for DC volts, and it'll measure AC volts for household use, and it has some current scales. And you have to read your instructions. When you're measuring current, a lot of times you have to put one of the test leads in a different connecting hole. So always read the instructions and become familiar with the meter you're using. So that was just a few bucks. In fact, if you watch your mail, if you shop at Harbor Freight and watch your mail for their little sales circulars, sometimes they give these away for free. So all you have to do is take your coupon in and go pick one up. And lastly, here's another cheap little meter. And you may laugh, oh boy, well that's old scale. It's got the little analog meter with the needle that goes across. And why would you even have that? Well, I'll confess, I just bought this for doing this lesson. I paid less than $10 for this on the internet. And again, you see it has two test leads. Has different scales. I haven't put batteries in this yet, so I can't show it zeroing out on ohms. This one, when you touch the leads together to check the ohms, okay, zero resistance, if it doesn't go perfectly to zero, you can adjust it. Usually with a thumb wheel like this, or sometimes there'll be you would do it with a screw here in the center. I haven't read the instructions on this yet. I'll get to that later when I have to use it. But there's a good reason to have one of these, because sometimes when you're checking a voltage that is momentary, it comes and goes and comes and goes, maybe like a turn signal circuit, this needle will react faster than the scale on the display on the digital meter. So this meter is actually more useful for looking at voltages like that, because you can see the needle deflect, and I'll show you that later on in another circuit or another lesson when we talk about turn signal flashers or something like that that's momentary. And you can see that movement, and you know that the circuit's working. So don't laugh, okay? You don't have to have hundreds of dollars tied up in test equipment, okay? For doing automotive electricity, in many cases, something like this for less than $10 will be fine. Well, that about wraps up lesson 1. I think I'll save the everything else for other lessons. Instead of making these videos real long, I'll try to keep them fairly short. This one may be one of the longer ones, actually. I thank you for watching. I hope that as I go through these lessons that they will be valuable to you, and if they are, please press the like button or even subscribe to this channel. I'd also like to invite you to join me and my friends at therangerstation.com. Come join the fun. Thank you for watching Livy's Ranger Garage.